holding in my hands a book that was written by a Scottish chemist called Sir William Ramsay, the man who discovered the least reactive elements in the entire periodic table, the noble gases. This is a second edition, which is particularly cool for a very specific reason that I'll explain later. It was printed over 120 years ago, and it's a magnificent story about the discovery of the gases in the atmosphere. By the late 1800s, it was well understood that air was not a single gas, but that it was a mixture of gases, mostly nitrogen and oxygen. In March of 1893, an English scientist called John Strutt, more commonly known as Lord Rayleigh due to his title as a baron, published a paper where he described his method for determining the densities of different gases, and he noted a strange anomaly. After successfully measuring the density of oxygen, he used a couple of different methods to obtain nitrogen in order to measure its density. One method involved removing oxygen from regular air by passing dry air over hot copper. Here, the oxygen reacts with the copper to form copper oxide, leaving behind atmospheric nitrogen. Another method involved the combustion of ammonia, which produces nitrogen. He measured the densities of both of these sources of nitrogen and consistently found that the atmospheric nitrogen was slightly denser than the nitrogen prepared from ammonia, or as he named it, chemical nitrogen. Now, the difference was only about 0.5%, but this was too big to be a result of experimental error, so it was puzzling to Rayleigh. After a bit of thought, he came up with a few possible explanations for this difference in density. 1. There might have been some residual oxygen in the atmospheric nitrogen. Since oxygen is heavier than nitrogen, this would increase the density of atmospheric nitrogen. 2. The chemical nitrogen from ammonia might contain traces of hydrogen. Since hydrogen is lighter than nitrogen, this would decrease the density of chemical nitrogen. 3. As well as the normal N2 molecules, the atmospheric nitrogen might contain some N3 molecules. As the N3 molecules are heavier than N2 molecules, this would increase the density of the atmospheric nitrogen. The first explanation was quickly disregarded because it would have required a relatively large amount of oxygen to cause such a difference in density. The second explanation was more reasonable, so he tested it by intentionally adding hydrogen to the nitrogen, then passing the mixture over red-hot copper oxide, which oxidizes the hydrogen to water. After doing so, the hydrogen was once again removed, but the nitrogen was the same density as it was before, so the difference in density couldn't be due to the presence of any hydrogen. The third explanation was also a reasonable one. It was known that oxygen could be converted into ozone by passing it through an electrical discharge, so he attempted to do the same to his samples of nitrogen to see if it had any effect on the densities, but they remained unchanged. No matter what he did, the atmospheric nitrogen remained 0.5% denser than the chemical nitrogen. Rayleigh was at a loss, but his paper caught the eye of the head of chemistry at University College London, William Ramsay. Ramsay had previously attempted to synthesize ammonia by passing nitrogen and hydrogen gas over various heated metals. Although this was unsuccessful, he found that red-hot magnesium was a very good absorbent for nitrogen, as it readily formed magnesium nitride. After reading about Rayleigh's strange anomaly with atmospheric and chemical nitrogen, Ramsay asked Rayleigh for permission to run some experiments on atmospheric nitrogen to find out if any portion of it was different from the rest. Rayleigh happily accepted, and Ramsay got to work setting up a beautifully elegant experiment. For 10 days, he passed atmospheric nitrogen back and forth between two gas holders, here labelled A and B. The gas passed through tube G, which contained the red-hot magnesium to absorb the nitrogen. The gas also passed through tube E, which contained red-hot copper to absorb any residual oxygen, and red-hot copper oxide to oxidize any hydrocarbons or dust to carbon dioxide and water. The carbon dioxide would then be absorbed in tubes F and I, which contained a mixture of soda, or sodium hydroxide, and lime, or calcium oxide, both of which are basic, so they would react with the acidic carbon dioxide. Any water would be absorbed in tubes D and H, which contained phosphorus pentoxide, a powerful drying agent. By the end of the 10 days, most of the atmospheric nitrogen had been absorbed along with any residual gases that were known to exist at the time. The apparatus was modified for a smaller volume of gas, and the experiment was continued for a few more days. Finally, after around 2 weeks, Ramsey was left with a tiny volume of gas which was around 1/80th of the volume of the atmospheric nitrogen that he started with. By weighing this unreacted gas, he found that it was around 20 times heavier than hydrogen. This allowed him to calculate that this gas made up less than 1% of dry air. The next step was to examine the emission spectrum of the gas. This is when you supply energy in the form of heat or an electric current to a substance and observe the spectrum of light that it gives off by dispersing it through a prism. Each element displays its own characteristic colored lines. We now know that these lines are caused by electron transitions within the atoms, but at the time the reasons for these lines weren't clear since the electron hadn't been discovered yet. Ramsey noted that the spectrum of this new gas contained groups of red and green lines which did not appear to belong to the spectrum of any known gas. Meanwhile, while Ramsey was performing his experiments, Rayleigh was himself continuing to work on the problem. He was working on his own method of removing the known gases from air. He did so by repeating experiments made by Henry Cavendish over a century earlier. The idea was to trap atmospheric nitrogen and oxygen in an inverted test tube over a solution of caustic soda or sodium hydroxide. By creating an electric arc in the test tube, the nitrogen will react with the oxygen to form various oxides of nitrogen, all of which are acidic, so they react with the basic sodium hydroxide solution below and are therefore removed from the test tube. When Cavendish originally did this in the 1700s, the volume of gas in the test tube gradually reduced until he was left with a small residue of gas that would not disappear upon sparking with oxygen. Rayleigh repeated this experiment and noted the same result, but he then used a spectroscope to observe the sparks and, just like Ramsey, saw a spectrum that didn't match up with any known gas. In his book, Ramsey says, "At this stage, the two discoverers joined forces and letters passed almost daily between them. They both scaled up their experiments and were able to isolate larger quantities of this new gas. They found that it was extremely unreactive and would remain unchanged after exposure to some of the most reactive substances, even in pretty extreme conditions. No matter what they tried, they couldn't get it to react with anything whatsoever." This inspired the name for the gas, Argon, after the Greek word for idle or lazy. It has the same root word as the word lethargy. Next, they carefully measured its density and specific heat, and by doing some very elegant calculations, they were able to determine that argon had a relative atomic mass of around 40. They were also able to establish that it was monatomic, meaning it floated around as individual atoms, as opposed to diatomic oxygen, nitrogen, and hydrogen. Now, 2 years before all of this, in 1883, two Polish chemists called Karol Olszewski and Zygmunt Wroblewski had become famous for being the first people in the world to liquefy oxygen and nitrogen. After the discovery of argon, Ramsey sent Olszewski a sample of this new gas. Using his novel cooling technique, Olszewski was able to freeze argon, which in turn allowed him to precisely measure its melting point and boiling point. These precise values gave further evidence that argon was indeed a pure element, since a mixture would have melted and boiled over a range of temperatures. Accounting for all of this, as well as its unique spectrum, it had been conclusively proven that argon was an entirely new element. The discovery of argon in 1894 was a huge deal in the scientific community, as it didn't seem to fit with any other elements in the periodic table. Every other known element had properties in common with other elements, but argon seemed to defy categorization entirely due to its extreme inertness. Over the next couple of years, Ramsey continued to try and get argon to react with something, anything. He began a search for a substance that released argon when it reacted, to give a clue as to what types of substances could bond with argon. This line of investigation led to another amazing discovery, but you'll need a little bit of backstory before we get into it. Almost 30 years before the discovery of argon, a French astronomer called Pierre Janssen traveled to India. A total solar eclipse was predicted to occur in Guntur on the 18th of August 1868, and he was keen to observe the spectrum of the sun's chromosphere. He set up his equipment, waited for the eclipse to occur, and, like clockwork, the moon passed in front of the sun exactly when predicted. Using his spectrometer, he examined the colourful solar prominences and he saw something interesting. The spectrum showed a clear line that had never been found on Earth before. There seemed to be a mysterious element that only existed within the sun. A few months later, a couple of English astronomers called Norman Lockyer and Edward Frankland observed the exact same inexplicable line when they looked at the sun's spectrum. Lockyer suggested the name helium after the Greek word for the sun, helios. It's interesting to note that the ending ium probably shouldn't have been used here, as it normally only applies to metallic elements, but Lockyer, being an astronomer, was probably unaware of chemical conventions. Lockyer would go on to found the famous scientific journal, Nature. Now, for years, this sun element wasn't thought to exist on Earth. Nobody could find it anywhere. That all changed in 1881. An Italian physicist called Luigi Palmieri was studying the eruptions of Mount Vesuvius overlooking what was once Pompeii. He collected samples that he found near the edge of a volcanic vent, and when he heated them up in his lab and examined the gas that they released with a spectroscope, he saw the distinct line for helium. This made Palmieri the first person to detect helium on Earth, although some scientists were still skeptical. Skipping ahead a few years to 1895, Ramsay was searching for a substance that contained argon. He learned that the American chemist William Francis Hillebrand had heated a rare mineral called cleveite and had collected a large volume of nitrogen from it. By this point, Ramsay had become an expert at analyzing nitrogen, so he sent off for a sample of the mineral and started investigating it himself. He heated it up with sulfuric acid, collected the gas that was produced, and used Rayleigh's method to remove the nitrogen and oxygen, hoping to be left with argon. But when he looked at the spectrum of this gas, he found that it was different to argon's. He compared the spectrum to the spectrum of the sun and found that he had discovered terrestrial helium. Ramsay got straight to work investigating its properties and found that it was very similar to argon. Like argon, it was extremely unreactive, and like argon, it was monatomic. In his book, Ramsay said that it is therefore reasonable to place it in the same class of elements as argon. So, suddenly, the completely unique element known as argon that didn't seem to fit anywhere in the periodic table had a sibling, helium. Ramsay said, after the discovery of helium, it appeared certain that other gases remained to be discovered. Now it was known that these inert gases could be found by heating different substances. A very large number of minerals were heated in a vacuum and the gases they gave off extracted. However, despite all his searching, Ramsay was only ever able to find more argon or helium. Ramsay suspected that the atmospheric argon might contain a small quantity of an undiscovered inert gas. He set out to liquefy a large volume of argon so that he could use a technique called fractional distillation to separate out anything that was in there. The idea was to very slowly raise the temperature of the liquid argon. Since different liquids typically boil at different temperatures, if there were indeed other elements mixed in there, they would boil at different temperatures to each other, and one by one they could be separated. There's a great article on Chemistry World about Ramsay's life, which describes his fierce rivalry with James Dewar, who is probably most famous today for his invention of the Dewar flask, also known as the vacuum flask. According to the article, to confirm the status of argon and helium, and to isolate any further atmospheric gases, Ramsay needed large-scale facilities for liquefying and fractionally distilling air. But Britain's leading expert in this field was his opponent, Dewar. Instead, Ramsay turned to William Hampson, with whom Dewar was also in dispute. Now, in 1895, Hampson patented an innovative process for liquefying gases, and he licensed it to Brin's Oxygen Company, which later became the industrial giant British Oxygen, now known as BOC. Hampson gave Ramsay some advice and a litre of liquid air, so Ramsay and his assistant, Maurice Travers, set off to build their own distillation apparatus, a lot of it improvised from recycled equipment. By this time, they had around 15 litres of isolated argon ready to liquefy and distill, but since it had taken them months to amass that amount, They wanted to use the liquid air that Hampson gave them for some preliminary experiments to see if they could find anything before risking their precious argon. On the 30th of May 1898, they very carefully increased the temperature of the liquid air and allowed most of it to boil off to see if the dregs contained any undiscovered gases. After removing oxygen and nitrogen from the leftover portion, they were left with a tiny volume of an inert gas. The density of this sample was significantly higher than that of argon, suggesting a heavier gas was mixed in there with it. They then examined it spectroscopically. Ramsey said, "While it showed the well-known argon spectrum, two brilliant lines were also visible, one in the yellow and the other in the green part of the spectrum. They gave this new inert gas the name Krypton, from the Greek word for hidden. It has the same root as words like crypt or cryptic." On discovering Krypton, they now felt confident to start investigating their 15 litres of argon to see if they could find anything else. A few days later, they got to work. Upon liquefying, their 15 litres of argon reduced to a volume of about 11 cubic centimetres. Just like with the liquid air, they very slowly increased the temperature of the liquid argon, and the first portion that boiled off, in other words, the gas with the lowest boiling temperature, was collected. This time, its density was found to be significantly lower than that of argon, indicating that it was made up of lighter atoms. What's more, its spectrum was completely unique. Another new element had been discovered. They named this one neon, from the Greek word for new. It has the same root word as words like Neolithic and Neoclassicism. They kept at it, performing countless fractionations of the portions they'd already isolated over and over again, trying to separate off something new. Eventually, they found that if the krypton fraction was isolated and pumped away slowly, it left a residue behind. This residue had a density even higher than that of krypton, indicating an even heavier atomic mass. They examined the spectrum of this residue and, once again, it was a new element. They named it Xenon, from the Greek word for stranger. It has the same root as words like xenophobe and xenomorph. Neon, krypton, and xenon were all shown to be monatomic and extremely unreactive, just like argon and helium. So, in a matter of days, Ramsey's inert gas siblings had grown into an entire family. 5 new elements, making up a brand new group in the periodic table. This really was amazing work. A few years later, in 1902, Ramsey was knighted. In 1904, Rayleigh won the Nobel Prize in Physics and Ramsey won the Nobel Prize in Chemistry, both in relation to their work on the inert gases. They were the first ever British recipients of these prizes. Now I'd like to show you why this second edition of Ramsey's book is so special. In his preface to the second edition, dated December 1900, so just 4 years after the publication of the first edition, he says the following. Since the publication of the first edition, atmospheric air has been found to contain other 4 inactive gases belonging to the same class of elements as argon. These are helium, discovered by myself in 1895 in certain rare minerals, but first separated from the atmosphere in 1900, and neon, krypton, and xenon. I mean, just imagine that. You discover a new element, write a book about it, and then 4 years later you're following up with a second edition which now details the discovery of 4 more elements. It truly was an incredible achievement. But the story doesn't end there. A few years earlier, on the 21st of December 1898, Pierre and Marie Curie discovered a radioactive element that was later named radium. In 1900, a German physicist called Frederick Ernst Dorn noticed that radium compounds emanate a radioactive gas that he named radium emanation, after a recent discovery by the New Zealand physicist Ernest Rutherford, who had found that thorium compounds also emit a radioactive gas which he called thorium emanation. Shortly afterwards, a French chemist called André-Louis Debierne discovered actinium emanation. Now, all of these emanations, despite being radioactive, were found to be extremely chemically unreactive, so they naturally drew the attention of Ramsey. By now, he was a master at isolating gases, so he performed an experiment over 2 weeks where he isolated some radium emanation from radium bromide. he noted that its spectrum had a striking resemblance in general character to the spectra of the gases of the Argon group. He suggested that this gas might belong to the same group as his recently discovered inert gases. In 1909, Ramsey published a paper where he went into more detail about the properties of radium emanation. When you look at the trends in properties of all the previously discovered inert gases, this new gas seemed to fit perfectly as the heaviest element in the trend. In a paper published in the French Academy of Sciences in 1910, Ramsey suggested the name niton from the Latin word for shining, due to the gas's luminescent properties. This name was initially accepted, and Ramsey uses it throughout the 4th edition of his book. However, in the 1920s, the International Union of Pure and Applied Chemistry, who to this day standardized naming conventions in chemistry, selected the name radon after radium, the element where this emanation had been discovered. By this time, the concept of isotopes had also been discovered, and it had been determined that the thorium and actinium emanations were actually just different isotopes of radon. Sadly, in these early days of radioactivity, nobody knew about the dangers of exposure to these substances. Ramsey was one such victim. After a lifetime of enormous contributions to chemistry, he died on the 23rd of July 1916 from nasal cancer at the age of 63. Ramsey was a brilliant chemist whose work affects us to this day. His inert gases eventually became known as the noble gases, and their unique sets of properties have given them various applications since their discovery. For instance, using an atmosphere of argon allows modern scientists to perform reactions that would otherwise be impossible in air. Liquid helium and neon are used as coolants for superconducting magnets and medical imaging. Krypton is used in high-performance light bulbs. Xenon is used as an ion thruster for spacecraft. Radon is used in radiotherapy to treat cancer patients. But perhaps the most obvious use of the noble gases is as beautiful glowing lights in glass tubes, illuminating city nights. So the next time you see a neon sign, just pause and take a moment to appreciate the amazing work that's gone into lighting it up. Leave a comment below if you'd like me to make a video about the discovery of any other elements, and if you enjoyed this video, I'd really appreciate you subscribing. Thanks for watching, and I'll see you in the next one.